So guys, today this video is going to be a follow-up video to our previous topic, the ones complement. Okay, you see, the scientists or the computer scientists, the mathematicians have actually devised a different method to use in a computer. It's called the 2's complement and its decimal equivalent is called the 10's complement. Now, to understand why that is more preferred over the ones complement or the 9's complement, we have to understand the shortcomings of that process. Okay, so let's get the video started. We are going to start at this point. Okay, a minus of b. In the last video we showed that we can convert this in the form of a plus of minus b, and there is no point explaining further, but you saw that it supports all numbers, right? But is that true? You see, we are going to look into a very special case right now. Okay, we are going to take a scenario, say a plus b and a minus b, and b will be equal to 0 basically. Okay, so this is the normal addition case. Okay, so in this case the b would be represented as 000 and as many number of bits there the computer can handle. Okay, but you see, in the case of subtracting b, we have to perform a complement operation, right? So what would be the complement of 0? Any guesses? I mean, we showed you the process, right? What was that? Exactly. We have to just flip the bits, right? So they become 1, 1, 1, and 1. Now, in your mind, you are thinking, like, what's the problem with this, right? But you see, the catch here is that, you see, 0 is neither a positive number or a negative number. It's simply 0. But here in this case, because of this complement process, we get that we have two values for 0. In when it is treated as a positive number, say in case of normal addition, it's simply all zeros. But when it is treated as a negative number, it becomes all ones. Now you see, in we have a restriction in the number of values we have. Let's say there are 4 bits to work with, 1, 2, 3, 4. So this basically has a range of 2 to the power n minus of 1. What this means is that this is the maximum value you can assign it. If n here is 4, so 2 to the power 4 minus 1, and that is 15. So with 4 bits you can go from 0 up to 15. Okay, now because of this complementary process and 0 having two different values, you see, we are getting one, we get to express one less number than this. That is very inefficient, and this is the major shortcoming of the ones complement process. So let's first look at this solution that the scientists have figured out, the 2's complement and its equivalent, the 10's complement. Let's first see the process. Okay, you see, if I have a binary number, say 1101, what we do is we first find its ones complement. Okay, so that would become 0010, and then by rule we have to add 1 to this. So this way this basically becomes 0011, and this is the 2's complement of this binary number. And likewise, in case of, say, the decimal system, let's take this number, say minus of 329. What we do is first we find this number's 9's complement. So that is basically 670, and then we add a 1 to it, and now that becomes 671. Okay, now we are going to get into the logic of why this solution works, but first this is the process of how it is done basically. Okay, so now let's see the 0 situation. Okay, but in 2's complement, you see, the first thing we have to remember is that a computer can only work with a fixed length of a number. A normal computer, say, handles up to 8 bits. Okay, So that would be 0 0 0 0 0 0 0, 8 bits of zeros. Okay, and this is how 0 is stored in the computer. Okay, now you see the maximum value the computer can work with or can store is basically 2 to the power 8 of minus 1 basically. So when you find the ones complement of 0, it would basically give you 8 ones, right? Right? So let's say now we use the same procedure to find its 2's complement. Okay, so what we have to do is we add a 1 to it. So let's perform this addition. So this becomes 0 0. There are carries everywhere in every step. 0 0 0 0 0, and finally a 1 comes down. But you see, since the computer can only store up to 8 bits, this final ninth bit gets discarded automatically because the machine cannot even store it. It can't even handle it. That is why you see all the remaining bits are 0. Isn't that right? And this is the solution of the 2's complement and why it is chosen basically. You see, it again loops back when 0 is complemented, it again loops back to the value 0. So now that means positive 0 and negative 0 both can be represented with only one particular value, that is all zeros. Isn't that neat, guys? So that was a neat solution, but the main point is, does the math hold? Does the operations work, right? So guys, let's get proving. Okay, I'm going to work on the tens complement, but the same logic applies to the binary system as well, the 2's complement. Okay, so back to the previous example that we shown in the previous video. Let's take two numbers, say 841, and I want to subtract that from say 329. Okay, and the output should give me 512. Okay, so let's see the process in action. Okay, so 841 remains the same, but we now find the tens complement of this, so that becomes 671. Back then it was 670, the nines complement, but we add a 1 to it. So now we perform the addition. So this will be 2 1 carry of 1 and a 15, and see, if a carry is generated, the carry is discarded, and that leaves the answer behind. Now this is the 2's complement subtraction process. The tens complement subtraction process, and the same process applies to the binary one as well. But we are going to see if it actually works in the back. Okay, what happens under the hood. So like previously, let's write this down. Okay, 841 plus of minus 329. This will give me a result of a variable. Okay, now let's perform the tens complement here. Okay, 841 plus minus of 329 plus 1000, and that is a plus 1000. Now why 1000? You see, in the nines complement we are adding 999, but in the tens complement we are also finally at the second step adding an extra 1 as well. That is why it becomes 1000. And I think you can already guess where the proof is going. It's almost similar to the previous one, right? So let's get rolling though. So this step becomes 841 plus 671, and on this side this is a plus 1000. Now what is this result? Remember, this was nothing more than 1512, and that is equal to a plus 1000. Okay, and remember, like the previous video, the same logic applies. When we shift the sides, say, so this now becomes 1512 minus of 1000, and it is because of this 1000 that we can discard the carry, and also this reason as well. 841 less than 1000 and 671 less than 1000. When both are added together, will be less than 2 times 1000. So this one value will all never exceed 1. It will always be less than 2. It will have no other value. And because of this reason and this 1000 here, we can confidently discard this carry. And now, so finally the output becomes 512. So you see, the math actually works. Isn't that neat, guys? So guys, with this I end this video, and I hope you put all your queries in the comment. Please like and subscribe to my channel and share my videos, okay guys? And one last thing to say, to learn, never memorize. Happy Holi, guys.